In the second lecture of this series, we're going to look at the different types of molecular orbitals you find involved in the carbon atoms in a wide variety of organic molecules. By the end of this lecture, you should be able to explain what is meant by hybridization with respect to molecular orbitals. You should be able to explain what is meant by the terms sp3, sp2 and sp orbitals. You should be able to recognise sigma and pi bonds, and you should be able to explain the bond lengths, bond angles and lack of rotation in alkenes with reference to sigma and pi bonds. So, let's look at the molecular orbitals in alkanes. And before we do that, we'll go back and let's look at the electron arrangement and the atomic orbitals in just our ordinary carbon atom. A carbon's got 6 electrons, so it's got an electron arrangement of 1s2, 2s2 and 2p2. And we know it forms 4 bonds, and the 4 electrons that are involved in these bonds are these 2 electrons here and these 2 here. So 2 of them are in s orbitals and 2 of them in p orbitals. So this might suggest that, so imagine you've got methane and this carbon's bonding with 4 different hydrogens, that the molecular orbitals would be different depending whether it was a hydrogen bonding with one of the p electrons or a hydrogen bonding with one of the s electrons. But in fact, that's not what we find. We find that all 4 of the molecular orbitals are identical. So in order to explain that slight oddity, we have to use the concept of hybridization in molecular orbitals, and that's what we're going to talk about mainly in this lecture. Right, so in each carbon atom, and this goes for all alkanes, what you get is the 2s orbital and all 3 of the 2p orbitals mixed together to form 4 degenerate hybrid orbitals known as sp3 orbitals. Now I'll try to explain that in a wee bit more detail. Right, so we're just showing the electrons that are involved in the bonding, so I haven't shown the 1s electrons which aren't involved in the bonding. So here's your carbon atom with the 2 electrons in the 2s orbital and 2 electrons in the 2p orbitals in separate orbitals with spin in the same direction as you'd expect. So what happens before the molecular orbital is formed is one of these s electrons is promoted, is excited into a 2p orbital, and then the 2s orbital and all 3 of the p orbitals mix together to form a hybrid of 4 hybrid molecules known as sp3. The sp3 means it involves an s orbital and all 3 p orbitals. Okay, so there's 4 of them, each one is an sp3 orbital. Okay, they're degenerate, they all have the exact same energy, and that energy lies in between the energy of the 2s and the 2p orbital. So let's read this top line again. So in each carbon atom, the 2s orbital and all 3 of the 2p orbitals mix together or hybridize to form 4 degenerate orbitals, each one being an sp3 orbital. Now here's the shape of the 2s orbital, and here's the shapes of the 2px, 2py, 2pz orbitals. The hybridized molecule though hybridized orbital has a different shape. So this is the shape of the sp3 orbital. So it's a bit like the dumbbell shape of the p orbitals, but with one side of the dumbbell being far bigger than the other side. And in fact, normally when we draw it, we just ignore the small bit. And this is the way we normally show the orbitals, the hybridized atomic orbitals in a carbon atom. So you've got 1, 2, 3, 4 sp3 hybrid orbitals, forming perfect tetrahedral shape, the bond angle being 109.5 degrees. So we do in fact have 4 identical atomic orbitals, which is why when it bonds with 4 hydrogen atoms we get 4 identical molecular orbitals. But that's only possible through this process of hybridization, which you must be able to explain. So once you have these hybridized atomic orbitals, how do they form a molecular orbital with, say for example, hydrogen atoms? Okay. Well, what we get is a end-on overlap of the atomic orbital of the hydrogen with the atomic orbital of the carbon. So if you imagine, here's your 4 sp3 atomic orbitals of the carbon, here's your atomic orbital for the hydrogens, and the hydrogens just overlap at the end of the sp3 orbital, forming what's called a sigma bond. So a sigma bond is characterized by this end-to-end overlap. Okay, so end-on overlap gives you a sigma bond. And so in your simplest alkane, methane, you've got 4 sigma bonds brought about by the end-on overlap of the hydrogen atom with the sp3 hybridized atomic orbitals of the carbon. And this is ethane, much the same, but the carbon-carbon bond is also a sigma bond. It's the end-on overlap of the sp3 orbital of that carbon with one of the sp3 orbitals of that carbon, forming this sigma bond between the 2 carbon-carbon atoms. So in alkanes, all the bonds are sigma bonds. Okay, so now let's contrast with the situation where you've got double, and next we'll go and look at triple bonds. So the situation is slightly different in alkenes. In alkenes, instead of forming 4 hybridized atomic orbitals, you only form 3 hybridized atomic orbitals. So these formed between the 2s orbital and just 2 of the 2p orbitals, not all 3 as in the previous case. So this is known as sp2 hybrids. That involves an s orbital and 2 of the p orbitals, not all 3. So here's our carbon atom in the ground state, 2 electrons in the 2s orbital, 2 electrons in the 2p orbital. As I said previously, the electron from the 2s orbital gets excited into the 2p orbital, and then instead of all 4 of those orbitals mixing together to give 4 sp3 orbitals, that s orbital mixes with just 2 of these p orbitals, forming these 3 sp2 hybrids. And one of the p orbitals just remains as a normal p orbital. It doesn't get involved in the mixing, doesn't get involved in the hybridization. So we've got 3 sp2 atomic orbitals and 1 remaining normal p orbital. So this is what the carbon atom would look like. The darker orbitals are the sp2 hybrids, 3 of them, 1, 2, 3, 1, 2, 3, and the white one is just the ordinary p orbital. Okay, so I've 1 electron in here, 1 electron in here, 1 electron in here, and 1 electron orbiting in that area there. So it's just a normal p orbital, that white one. So, as before, the hybrids form sigma bonds. Okay, so this is looking at the ethene. So you've got a carbon atom there, a carbon atom there. This carbon forms 3 sigma bonds by end-on overlap. One with the hydrogen, second one with the hydrogen, and the third one with this carbon. And the same with this carbon. 3 sigma bonds, one with the hydrogen, one with the hydrogen, and one with the carbon. Okay. But obviously they form 4 bonds. So the 4th bond is going to involve the p orbital, the non-hybridized p orbital. Okay. And we know it forms a double bond, so it's going to bond with the electron in this carbon atom. It's going to bond with the electron or combine with the electron from this carbon atom to form the 2nd bond. But they can't do it as a sigma bond. You can't get the end-on overlap of these orbitals. Okay. So the normal non-hybridized p orbital, they merge together above and below the plane, forming what's called a pi bond. So this picture tries to show this. So the grey molecular orbitals are just the ones involving the sp2 hybridized, and then the 2 p orbitals which are on each carbon then sort of bend over towards each other, overlapping sideways. It's normally referred to a side-on overlap as opposed to an end-on overlap. It's sort of side-on overlap. So above and below the plane of the molecule. So it's called a pi bond. So it's formed by the sideways overlap of 2 parallel atomic orbitals lying perpendicular to the axis of the bond. So you have to be able to differentiate between the sigma bonds, which are end-on overlap, and the pi bonds, which are sort of the sideways overlap. Okay, so in an alkene then, one of the carbon-carbon bonds is just a normal sigma bond, but the second one is a pi bond. Okay, and all the carbon-hydrogen bonds are sigma bonds. The structure of an alkene is planar. All the carbons and hydrogens lie in a plane. It can't rotate, however, because of the pi bond. The pi bond stops rotation, so it doesn't rotate round the way an alkane would. Okay. So the pi bond prevents rotation, and that will be important when we look at stereochemistry in section 2.3. We'll come back to that. And the pi bond is actually weaker than the carbon-carbon pi bond is weaker than the carbon-carbon sigma bond. When we draw it in this normal format, the 2 bonds look identical, but in fact they're not. The sigma bond is stronger than the pi bond because the degree of overlap is more. That end-on overlap is, you get more overlap than just in the sideways, so it's a stronger bond. Okay, let's look at what happens in the homologous series you haven't met yet, the alkynes, and that's where you get a carbon-carbon triple bond. And the first member of that series would be ethene, which has got a carbon-carbon triple bond. So in this case you get hybridization again, but in this case it's just the 2s orbital and only one of the p orbitals, and that's known as an sp orbital. Okay. So this is a sp orbital. Okay. So it involves the s orbital and only one of the p orbitals. Occasionally you might see it referred to an sp1, but it's no more normal just to write it as an sp orbital. So here's your carbon atom in the ground state. The 2s electron, one of the 2s electrons gets promoted to the 2p orbital, and then the hybridization process involves the 2s electron, 2s orbital, and just one of the 2p orbitals. So you get only 2 hybridized orbitals, and you've got 2 normal p orbitals left over. So, as before, the hybridized orbitals form sigma bonds with end-on overlap. So that carbon CH bond there would be a sigma bond, and one of these carbon-carbon bonds would be a sigma bond formed by the end-on overlap of the hybridized orbitals. Again, this carbon, it's got one there and one there. But the other 2 bonds in this case, so there's the sigma bonds. But the other 2 bonds in this case will be pi bonds. Okay, so the red ones are the pi bonds, and they are from the sideways overlap of the non-hybridized 2p orbitals. Okay, so to summarize, in alkanes, the atomic orbital is 4 sp3 orbitals. So it involves 1 s and all 3 of the p orbitals. In an alkene, it's sp2 hybridization, and in an alkyne it's just an sp hybridization. And we look at the effect on the carbon-carbon strength of the carbon-carbon bonds. Well, in the alkane, the bond is a sigma bond. In the alkene, one of them is a sigma bond, but the other one's a pi bond. And in the alkyne, only one of the bonds is sigma and 2 of them are pi bonds. The bond length gets shorter. The more bonds you have between the 2 carbons, the closer they're going to be pulled together. But if you look at the energy required to break the bonds, obviously the more bonds there are between the carbon atoms, the more energy is required. But you'll notice that the carbon-carbon double bond is not twice the carbon-carbon single bond, it's less than twice. So if both the sigma and the pi bond were equal strength, we expect the mean bond enthalpy for the carbon-carbon double bond to be 740. It's only 602, which shows that the pi bond is weaker than the sigma bond. And again, we see the same pattern with the alkyne. So the pi bond is not as strong as the sigma bond. Okay. So quite a lot of theory there to get your head around. You have to explain what is meant by SP, SP2, SP3, recognise sigma bonds and pi bonds. So it might be a lecture you want to go back and look at again. Let's finish by just looking at a quick question. Okay. So, which line in the table is correct for the following hydrocarbon? So you have to identify how many sigma bonds and how many pi bonds are in this molecule. So how do we think about that? Pause the tape and start it up again once you think you know the answer. Okay, so let's see how many sigma bonds there are. So the carbon-hydrogen bonds are always sigma. So we must have 1 there, 3 there, and 2 there. And on top of that, one of the carbon-carbon bonds is also a sigma bond. So 1 there, 1 there, 1 there, and 1 there. So that adds up to 2, 5, 6, 7, 8, 9, 10. So the number of sigma bonds is 10. And then when you have double and triple bonds, first bond is sigma, the rest are always pi. So here we've got 1 pi bond, and in the triple bond here we've got 2 pi bonds. So there's 3 pi bonds, so the answer was D. So by now you should be able to explain what is meant by hybridization with respect to molecular orbitals. You should be able to explain what is meant by the terms sp3, sp2 and sp orbitals. You should be able to recognise sigma and pi bonds, and you should be able to explain the bond lengths, bond angles and lack of rotation in the alkenes with reference to sigma and pi bonds.